Okay, this lecture is on the chemical content of life. So we're going to be talking a little bit about chemistry, and I have a periodic table you need to probably run off. I'll put it up on your eCampus. So the definitions: matter. Anything which occupies space and has mass is matter. So you know that all this stuff, like metals and wood and air is made up of matter. It's different components of gases, these different elements. Even light is matter. Light's made up of units of matter called photons. They're extremely small and extremely light, but light is still matter. On the periodic table, there are 92 naturally occurring elements that occur natural in nature. Now, we have man-made ones that are also on that table, but of that table, on that table, there are 92 that occur naturally in nature. Now, an atom is the smallest unit of ordinary matter that constitutes a chemical element. So that periodic table of the elements, those are atoms of the different elements. If you look at it, you'll see that hydrogen's number 1, helium's number 2, and so on. Atoms can be put together to make molecules. That's the emergent properties. The atoms have their own chemical and physical properties, but when they're put together with 2 or more of them being bound together, 2 or more atoms make up a molecule. Now that molecule has its own chemical and physical properties. Compounds are 2 or more different elements in a fixed ratio. So they're not going to be the same atom, be 2 or more different ones. Like water is H2O. That means there's 2 hydrogens, 1 oxygen. Carbon dioxide is CO2. 1 carbon, 2 oxygens. Sodium chloride, NaCl. That's sodium and chlorine. That's 2 elements. So compounds are 2 or more different elements in a fixed ratio. Now the definition of molecules was 2 or more atoms bound together. So all compounds are molecules because they're made up of 2 or more different elements. But not all molecules are compounds because molecules like oxygen, that's O2, those are the same element. That's not a compound. Hydrogen gas, H2, that's a gas, that's the same element, 2 hydrogens, so they're not compounds. So all compounds are molecules, but not all molecules are compounds. Now the emergent properties that I'm mentioning here can be seen with this sodium chloride. So look at the next slide. Here we have a metal, it's called sodium metal. It's a toxic metal. It ignites when exposed to water, so it has to be stored in oil. Chlorine is a toxic gas. It will kill you if you breathe it. But when sodium and chlorine are put together in a 1-to-1 ratio, sodium chloride, that makes table salt. And we use that to season our foods, French fries, We have a 0.9% sodium chloride content in our blood plasma, so it's slightly salty. So you see that the properties change from a toxic metal, toxic flammable metal, and a toxic gas. When they're joined together, the chemical and physical properties of sodium chloride are different. They're not as toxic in low levels. Here is showing the building up. Remember we talked about the atoms, which are not shown here, making molecules, and molecules make the organelles, which make the cells, which a lot of cells make up tissues, tissues to organs, and organs to organ systems, and all the systems to make the organism. So here's a hierarchy here, and everything changes. That tiger has none of the same chemical and physical properties as oxygen, carbon, hydrogen, or oxygen that make it up. It is a combination. It's more complex. Its chemical and physical properties are its own. They're not anywhere like the individual atoms that have made it up. So that's emergent properties there. the elements of life. Life as we know it, and you in particular, are made up of 96% of these 4 elements here. These elements are abbreviated. These are the chemical symbols for the elements. C is for carbon, H is for hydrogen, O is for oxygen, and N is for nitrogen. So 96% of life as we know it are made up of these 4 elements, mostly these 4 elements. About 3% is the next line. This is phosphorus for making adenosine triphosphate, for making DNA and RNA. Sulfur, the S is for sulfur for making proteins. Ca is calcium for bones, teeth, blood clotting, muscle contractions. K is potassium. K is, there's so many P's, the symbols have to be different, so they chose a Latin term. Kalium means potassium, and so they used the K. The next one is sodium. They had to use natrium, N-A-T-R-I-U-M, which is sodium in Latin. Had to use that one for sodium. Cl is chlorine. Chlorine is an electrolyte also, and magnesium, electrolyte, is used for your enzymes. Magnesium, Mg. So that's about 3% of you is made up of those elements on that line. And the trace elements, you have a smaller amount, like around 1% in your body, of iron. Fe is ferrous. It's Latin. Ferrous means iron. And this is used like the main thing you would be aware of is hemoglobin requires iron. When a person is anemic, the doctors usually put them on an iron supplement so that they can produce hemoglobin, the molecule that carries oxygen in your red blood cells. I is iodine, and iodine is extremely important for your thyroid to make your thyroxine and triiodothyronine, which controls cellular metabolism. And copper is important enzyme for certain important metal for certain enzymes. On this page, we can see there are 2 fields of corn plants here. The one on the left has had a supplement of nitrogen, so it has more nitrogen in its fertilizer than the one on the right. And you can see that they're taller and they're greener. They're going to be a little bit more productive because of the nitrogen supplement that's been added. This lady on the right, she has an iodine deficiency. So you see that her thyroid, which is in your neck, is swollen. It's atrophied. I mean, it's hypertrophied. I'm sorry, hypertrophied. It's gotten larger to try to glean more iodine out of her blood. If you put her on an iodine supplement like iodized salt, that will reduce in size and possibly even go away. So she has an iodine deficiency. That's why if you look at the store, you have several different versions of salt now. Used to, for the pioneers, they iodized the salt to make sure that they got iodine in their diet when they salted their meat and their food, and they didn't get goiter as they're progressing across the country. Now we get plenty of iodine in our diet, and they have plain salt, which doesn't have iodine, and we use sea salt, which is different also. Now, talking about atoms, atoms have several basic parts, and the 3 basic parts of an atom are the protons, neutrons, and electrons. Now, the atomic theory, which was developed, which discovered or named these components of an atom, there was a person that was involved in determining their mass, and his name was John Dalton. And the mass of a proton was given 1.07 Daltons, named after him. Now, another term, if you don't want to use Dalton, is atomic mass unit, or we just call it mass. So a proton has a mass of 1. Neutrons, they have a mass also of 1. Electrons are extremely small, and their mass is 1/1800th of an atomic mass unit, or 1/1800th of a Dalton. So this is the mass that was determined for these different components of an atom. Now I wrote down here what a Dalton is, just to show you how small it is, how many zeros past that decimal. It's 1.7 times 10 to the minus 24th grams. extremely, extremely small. Now, more information about the atomic structure. There's the center of the atom is called the nucleus. And you look at both of these drawings here, you see there's a nucleus, a center part here, and there's a ring or a shell around the nucleus. So let's look at the definitions over here again. We have a nucleus of protons and neutrons. We have electrons, but electrons are not in the nucleus. They're going to be in these shells or orbitals, and they have the negative mark there. So let's look down at this chart. Proton mass of 1. Things have changed on the chart. The charge is positive, and the location is in the nucleus. So when you look at both those drawings, one is the cloud form on the left and the shell on the right. They both have a particle in the middle that has a plus on it. Those are protons in the nucleus. Neutrons have a mass of 1, and they're neutral. They don't have a charge, and they're also located in the nucleus. So the other spheres you can see there, the darker shaded spheres in the nucleus, there's not a positive or negative sign on them. They're neutral. But protons and neutrons are both located in the nucleus of the atoms. Electrons, 1/1800th of a atomic mass unit, they're negatively charged, and they're outside the nucleus. They're going to be in these shells. And so you see the little structure with a negative sign. That's an electron in a shell. And then the one on the left, you see that's a cloud form, so you still see the electrons in the cloud. Now these shells can be called orbitals or energy states and whatever. We call them energy shells or energy levels. And the electrons that are in these different shells have certain amounts of energy stored in them. We'll talk about that in just a minute. So 3 basic parts: protons, electrons, and neutrons. Protons and neutrons in the nucleus, electrons in shells or orbitals that circle around the nucleus. Now, this picture here is to show the shells or levels that we'll be looking at for our explanation of bonds and where the electrons and atoms are found. And you can use the K shell, L shell, M shell, or N shell if you want to, or you could call it the first shell, second shell, third shell, and this one's not showing the fourth shell out, a little bit further out. We are going to go with the first shell can hold a maximum of 2 electrons. That's all that can be found in the first shell. The second, third, and fourth can have a maximum of 8 electrons in their shells. We are not going to look at suborbitals or anything like that. This is just really, really, really basic. So these shells fill sequentially. So when the first shell has 2, any more electrons that the atom has are going to have to go to the second shell until it's filled, and then they go to the third shell. So we'll talk about how many electrons each atom has in just a minute. But the shells fill sequentially from the first. When it's full, electrons have to go to the second. When it's full, then they go to the third. Now, I have down here, energy is the capacity to cause change. Okay, so let's look at the word potential energy. Is the energy that matter has because of its location or structure. The electrons of an atom differ in their amounts of potential energy. An electron's state of potential energy is called its energy level or electron shell. Now, looking at this example here, let's look at the left-hand side of this picture that shows the nucleus and the electron shells, and you see the arrows going out, energy absorbed. Electrons can absorb energy, and when they do that, they move to outer shells. Now, that's a temporary thing. And when the energy absorption stops, they decay back down, the bottom right-hand side of that picture, energy lost, and they decay back down to the shells they came from. Again, the first having only 2, the second can have a maximum of 8, the third a maximum of 8, and they fill sequentially. An example of this that you've probably seen before are the little stars you can buy for your children. They're little green stars you put on the ceiling, and when the lights are turned on, you don't really see them too much. Energy is being absorbed by the electrons in those molecules, whatever's in there, and they're moving to higher energy levels. When you turn the light off, they start decaying back down to lower energy levels, and they're giving off energy in the form of light. That's why they glow. So that's an easy example of seeing or understanding how energy can be absorbed and released by these electrons. You can actually see that. Now the shells. I have 3 shells here. I don't have the 4th one on here. I'll have to make a new slide set for that. But the first shell, you can see, has a maximum of 2 electrons. And they're the black ones in the first shell. Maximum of 2. The second shell has a max of 8. Now I paired them here just for counting convenience. They're not paired. Because like charges repel each other. So I just did this so you can see that there are 8 in this outer shell. For the third shell, it holds a maximum of 8. I paired them too, so it's easy to count them. You can see there's 8. And you know the 4th shell can hold a maximum of 8. But we really only look in this class at the 4th shell for one atom. That's going to be calcium, which is element number 20. So you can see that the shells hold a maximum. First holds a maximum of 2 electrons, second a max of 8, third a maximum of 8, and they fill sequentially. Some definitions. This is what we're going to cover on the next few slides here. So let's look at what you can find. Get your periodic table. You can find this helium, and let's look at that. All right, here's helium. It's element number 2. It's in the upper right-hand side of your periodic table. And that 2 is the atomic number. All of these elements on there have different numbers. The numbers are unique. Hydrogen element number 1, its atomic number is 1. That tells you the number of protons in the nucleus of an atom. Well, helium has 2 protons. That's what makes it helium. So anywhere in the known and unknown universe that there are atoms that only have 2 protons in their nucleus, that element is helium. Okay, so that atomic number is the number of protons in that the nucleus of that atom, and that tells you what that delineates or gives it those chemical, physical, and properties. By having only 2 protons, it's unique. It has its own chemical and physical characteristics. So the atomic number is the number of protons. You'll look at your periodic table, and you'll see that each one of them has a different number. That's what makes them different, the number of protons. So atomic number is the number of protons in the nucleus of the atom. The atomic mass, that's the lower number. You see, I put it in blue, just like I put the wording in blue. That's going to be the number underneath that chemical symbol, helium. It's the number of protons and neutrons in the nucleus of the atom. So this is both protons and neutrons total numbers in that element is 4. So with helium, if you know that it has 2 protons, that's the atomic number, and that the mass is the number of protons and neutrons, then you just subtract the number of protons from the atomic mass, and you get 2. Helium has 2 protons and 2 neutrons in its nucleus. That's its mass. Now I put in here atomic weight is not equal to atomic mass. And this is something that everybody uses like they're the same thing. I'm just going to let you know that they're really not. An example of that is I have a weight here on Earth. I'm roughly 160 pounds. Now if you transported me to the moon, my weight is going to be different because there's less gravity on the moon. I might weigh 110 pounds on the moon. My mass is the same. My mass on Earth is the same as my mass on the moon, but the gravitational pull is different, so my weight's going to be different. So that's the difference between weight and mass, even though everybody pretty much uses them as equal terms. Isotopes. Now an isotope says atoms of an element that have more neutrons than other atoms of that element. Well, you know what makes the element that element is the number of protons, right? The number of neutrons doesn't make that element, but it makes it an isotope of that element. So the most common form is the first one here, hydrogen. has an atomic mass of 1. That means that it has 1 proton. Look at my little picture there. Atomic number is 1, the mass is 1. So if the mass is the combined number of protons and neutrons, well, there are no neutrons because this atomic number is 1 and the mass is basically 1. But there are other forms of hydrogen. There are isotopes. One's called deuterium. Duo means 2, has a mass of 2. So it has 1 proton and 1 neutron. So the mass would be 2 on that one. But there's a third one called tritium. Tri means 3, atomic mass of 3. 1 proton and 2 neutrons. It's always going to have 1 proton because it's hydrogen. What makes the isotope is the number of neutrons. Now ions are charged atoms, and we're going to look at ions. In another couple of pages we'll look at ions, but they're charged atoms, and we'll see how that happens. He says ions are formed when an atom either gains or loses electrons. Okay. If the outer shell is half or more filled, the atom will tend to hold on to its electrons. Well, that's true. It'll tend to hold on to them. If the outer shell is less than half filled, the atom will lose electrons from its outer shell. So less than half filled means like 1 or 2. It can tend to lose those in its outer shell, especially if it's the second or third or fourth shell, because the maximum they can hold is 8. If they have more than half or more, they'll hold on to them. But if they have less than half, 1 or 2, they're going to tend to lose them and form charged atoms, which are called ions. Here is an example. If you look at your periodic table, you can find sodium, element number 11, and chlorine, element number 17, and you can see that they have sodium has 11 protons and chlorine has 17 protons in its nucleus. Now I just show nucleus there. Well, in a neutral atom of each of these elements, a neutral atom, the number of electrons equals the number of protons. So sodium, if you look over here on the left, it has 11 protons. It's going to have 11 electrons. So 2 in the first shell, 2, 4, 6, 8 in the second, that's 10, and 1 in the third, that's 11. That's a neutral atom. Let's look at the right-hand picture. Chlorine is element number 17. A neutral atom has 17 protons and 17 electrons. 2 in the first shell, 8 in the second, that makes 10, and 2, 4, 6, 7 in the third, that makes 17. That's a neutral atom. Well, according to the rules, if the outer shell is less than half filled, the element will tend to lose those electrons. And if the element is greater than half filled, which is chlorine is 7 out of 8, it'll tend to gain electrons. And so what this is showing is that sodium will tend to lose that electron. And so now sodium is going to have 11 protons, which are positively charged, and 10 electrons, which are negatively charged. It has 1 more positive charge than negative, and we're going to see that on the next slide. Chlorine had 17 protons, and 17 electrons, 17 negative charges. It used to be neutral, 0. Now it has 18 electrons, 1 more negative charge than positive, and it's going to be negative. So let's see what happens. Sodium is going to lose its electron. Chlorine will gain electron. Go to the next slide. Here we have the ions. You see that sodium is positive now. Its outer shell is full. The outer shell is called the valence shell, and its outer shell is filled now. Look at chlorine. It's a negative ion. Look at its outer shell. It's also filled. These are ions. They're charged atoms. Now, drawing these shells, if you're having any trouble, I put the next slide has some examples. Here's some electron shells that are already drawn according to your periodic table here. Here's hydrogen. It's got 1 electron in this first shell. Helium, on the right-hand side, there's 2. It's element number 2. It's got 2 electrons. Let's look at carbon in the middle there. For some reason, this 6 is on the bottom. It should be on the top. Element number 6 is carbon. It has 6 protons, and it's going to have 6 electrons, 2 in the first shell, 4 in the second shell. Let's look at oxygen as element number 8. That means a neutral atom has 8 electrons, or 8 protons, has 8 electrons, 2 in the first, and there's 6 in the second. Now, both of these would like to have their outer shells filled. And so you see that carbon only has 4. It would like to have 8. So it can form 4 bonds. And a bond means where it's going to share an electron with another atom, and it shares its electron with carbon. So we're going to talk about some bonds in just a minute where you have sharing of electrons to fill these outer shells. So carbon has 4 vacancies there, so it can form 4 bonds. You look at oxygen, it has 2 vacancies. It needs 2 more electrons to fill its outer shell. It can form 2 bonds. If you look at nitrogen, it has 3 vacancies there, so it can form 3 bonds. The bonding. All right, it's going to all these things are going to be involved in bonding. So let's just this is stuff we're going to talk about on the next slides. Bonding. Electron configuration, the use of shell diagrams. That's what these things are called, is shell diagrams, to show the location of an atom's electrons in relation to the nucleus. So you can see that this first atom on the left, its outer shell is filled. It has 2 electrons in it. That's going to be helium. The middle one here, it has its first shell's filled with 2, and the outer shell has 4. So that's going to be has 6 electrons. That's going to be carbon. You see that it could use 4 more electrons to fill its outer shell. So we'll see how that works. And the one over here has 2 and 8, 10, 11. That's sodium. So we'll see that the shell's filled sequentially. The first one's filled with 2, second one's filled with 8, and that single one's on the outside by itself. Those are shell diagrams for drawing these elements. Now, chemical bonds, the result from the interactions of electrons between the atoms. Originally, this was an animation, and it shows it would show this. The one on the left was hydrogen with 1 electron in its outer shell, and the one on the right was a hydrogen with 1 electron in its outer shell, and the one in the middle is oxygen with 6 electrons in its outer shell. Well, what happens is each of these hydrogens is going to share its single electron with oxygen so that it can have its outer shell filled. At the same time, an electron from oxygen's outer shell will be shared with each hydrogen to fill its outer shell. And so you can see that at any one point in time, each of the hydrogens has 2 electrons in their outer shells, and at any one point in time, the oxygen has 8 electrons in its outer shell. Now these electrons are being shared, and they're moving at the speed of light. So it's not like, you know, one's going to be losing electrons, one's going to be gaining electrons. It's not. If I were standing still in the classroom, and I could move around the Earth at the speed of light, I would see myself before I disappeared. We're talking about a level that we can't even see, and these electrons are moving basically at the speed of light, so at any one point in time, they're anywhere. And this forms water, H2O. That's H2, it says 2 hydrogens. There's one on the left and one on the right, and there's not a 1 ever put there, 1 oxygen, that's the one in the center. So they can form bonds by sharing electrons in their outer shells. Here are some molecules, 2 or more atoms bonded together, forming molecules. Molecules of oxygen is O2. There's 2 oxygens together. So the one on the left is sharing 2 electrons with the one on the right. We'll talk about bonds in just a little bit. That'd be a double bond. CO2, that's 1 carbon and 2 oxygens. H2O, that's water, 2 hydrogens, 1 oxygen. And this last one is glucose. We'll be dealing with this one a lot in this class. C6H12O6. That means there's 6 carbons, 12 hydrogens, and 6 oxygens make up that molecule. Now again, all these are molecules, but they're not all these molecules that are here are not molecules, are they? Some of them are compounds, but they are molecules. So all compounds are molecules, but not all molecules are compounds. Oxygen is not a compound. All of these are molecules, but they're not compounds. Compounds are two or more different. Carbon dioxide, carbon and oxygen. Water, hydrogen and oxygen. Glucose, carbon, hydrogen, and oxygen. Those are all compounds, but they're molecules. Oxygen's a molecule, but it's not a compound. So all compounds are molecules, but not all molecules are compounds. Now the valence electrons, they're the electrons in the outermost shell. So it says the outermost electrons of an atom. These are the ones that are involved, usually, in the formation of bonds. I have usually there because ions do not share electrons. Elements with a full valence shell are chemically inert. They are ions. They do not form bonds by sharing electrons. They're attracted by charges. Positive and negatives attract each other. Now the octet rule, octa means like octopus, or octagon means 8. It's the rule of 8. After the first shell, the second, third, and fourth electron shells contain 8 electrons. That's the octet rule. Now there's something called electronegativity, and it says the attraction the nucleus has for electrons. Now these are the only ones that we didn't even talk about, because we don't use all the elements on that periodic table. We only use the ones that I showed you on the first couple of slides. Oxygen is, carbon, hydrogen, oxygen, and nitrogen are, you're made up of 96% of those. Well, oxygen is real important. It has the greatest attraction. The nucleus of oxygen has a real strong pull on electrons of other molecules or atoms. And this is called the electronegativity. So just got to remember that it has the strongest electronegativity of any of the elements that we're going to be talking about in this biology class. It's 3.5. Okay, that's just a number. I'm not sure how they came up with that, but that's the largest number here. So it's got the greatest attraction for pulling electrons toward its nucleus. Nitrogen, electronegativity of 3, slightly less than oxygen. So both of those are pretty strong. Sulfur and carbon, 2.5, getting weaker. Phosphorus and hydrogen, 2.1, the weakest. So hydrogen bonds are pretty weak here. When you talk about hydrogen bonds, very strong, very weak electrostatic attraction for electrons. Molecular formula versus structural. Well, on the left-hand side, that's the molecular formula. You just write it out, and it tells you how many of each of the elements are in that molecule. 2 carbons, 6 hydrogens, 1 oxygen. But knowing that carbon can form 4 bonds because it needs 4 electrons in its outer shell, hydrogen can only form 1, and oxygen can form 2, you have to look at these structural formula and see that they can form 2 different patterns here. Carbon, you see these single lines, the single lines from carbon to hydrogens and carbon to oxygen means 1 pair of electrons is being shared between the carbon and the hydrogen, even between carbon and oxygen is sharing one pair of electrons. A pair is 2, right? I didn't put a little line between the oxygen and hydrogen because it made the molecule a little bit longer, but there's one in between there also. You look at the bottom one and you see that carbon, I told you, could form 4 bonds, so there's 1, 2, 3, 4. Hydrogen can form 1, so each one just has 1. Oxygen can form 2, so there's 1 with that carbon and 1 with the one on the right. Now, they both have the same molecular formula, but they are both different molecules. They're structurally different. Structure is very, very important to the characteristics of a molecule. The one on top is an alcohol, has an OH. This is ethyl alcohol, ethanol. This is the alcohol in beers and wines. The one on the bottom is called dimethyl ether. Now, ether is extremely flammable, extremely explosive in vapor form, and extremely toxic. 2 different characteristics. The ethanol you can drink in low levels, but it is toxic, has a low flame, low flammability, it's not explosive. The one on the bottom, you cannot drink that, it will kill you. It is very explosive, especially in the vapor form, it can explode. So it's not very stable. Explosive means if a spark ignites, it's very flammable, very flammable. So the structure and the formula are different. Now talking about bonding, covalent bonding, the sharing of electrons between the outer energy shells of bonding atoms. Those are the electrons in the valence shell. Those are the only ones that are involved in the bond. Electrons are shared. That means that the bond can be formed, but when the bond's broken, everybody gets their electrons back. So electrons are shared to fill the outer energy levels of both atoms. That's what I was telling you earlier. Remember, hydrogen has one electron in its outer shell, has one proton, one electron, but it would like to have two. So this molecule of hydrogen gas you see here, each one is sharing an electron with the other one. And so at any one point in time, there are two electrons in each of their outer shells. And that single line is one pair of electrons, two. Well, look at the one below there, water. You remember oxygen's element number 8. And so it has 2 in the first and 6 in the second. It would like to have 2 more electrons. Well, each of those hydrogens is sharing their electrons with oxygen, so that oxygen will have 8 in its outer shell, and oxygen sharing 1 of its with each of the hydrogens, so that it has 2. So at any one point in time, each hydrogen has 2 electrons in their outer shell. At any one point in time, the oxygen atom has 8 in its outer shell. You see how it's drawn. There's single bonds between oxygen and hydrogen, one pair of electrons. Just like a pair of shoes is 2, a pair of electrons is 2. Look at the top right. Remember, oxygen is element number 8, right? 2 electrons in the first, 6 in the second. Well, it needs 2 more electrons to fill its outer shell. So it's going to borrow 2. Each one's going to borrow or share 2. So the one on the left borrowed 2 electrons from the one on the right. Now it has 8 in its outer shell. You count 2, 4, 6, 8. At the same time, the one on the left side shared 2 electrons with the one on the right. And now the outer shell on the one on the right has 2, 4, 6, 8. Since there were 2 electrons that were shared between these atoms, that's 2 pair. And you see the double line there. That's 2 pair of electrons. Double lines represent a double bond, 2 pair of electrons. This last one in the bottom right, you see carbon. And you remember carbon's element number 6. 2 electrons in the first shell and 4 in the second. It would like to have 8. So carbon will share an electron with each of these hydrogens to fill their outer shells, and they share a hydrogen with each hydrogen shares an electron with the carbon to fill its outer shell. So looking at the drawing here, you see that each hydrogen has 2 in its outer shell, and the carbon has 8 in its outer shell. Now this is covalent bonding. It's bonding of sharing of electrons between atoms to fill their outer shells, to fill their valence shells. It says shared. So when the bond is broken, nobody gains or loses electrons. Each of the atoms walks off with the same number of electrons that it came into the bonding with. Now, there's something called a polar bond. This is because of the electronegativity of oxygen or nitrogen, and the one we're going to look at has to do with oxygen. It's the unequal sharing of electrons. An example is water. Oxygen, I put O2 just because that's oxygen, a molecule of oxygen, is more electronegative than hydrogen. Remember, hydrogen was 2.1, oxygen was 3.5. Oxygen has a greater affinity for electrons than hydrogens do. And so that's going to tend to explain why water is a polar molecule. So let's look at the next slide. Here's your oxygen, the big red sphere. Here's your oxygen atom. And you can see that there are hydrogens, 2 hydrogens below, and it shows arrows pointing toward oxygen. That means that the electrons are being pulled toward oxygen more than they're being allowed on the hydrogen side, which explains that S with the negative on the oxygen side. That means slightly negative, and on the hydrogen, slightly positive. Since the electrons of hydrogen are shared with oxygen, and oxygen shares with hydrogen, but the electrons cycle around oxygen more than they cycle around hydrogen, and so this molecule tends to be polarized. There are more negative charges in the area of the oxygen at any given time than there are in the presence of the hydrogens, because when you take the electron away from the hydrogen, it's just a proton out there. And so this molecule is a polar molecule, Electrons tend to be pulled toward the oxygen more than they're allowed on the hydrogen side, and so the oxygen side is more negative, slightly negative, and the hydrogen side of that molecule is slightly positive. So it is a polar molecule because of the electronegativity. Chemical bonding. Okay, this is going to be these next couple of slides here. Ionic bonding and ions. So we're going to talk about those on the next couple of slides. Ionic bonding results, a bonding that results from the attraction, results from one atom losing electrons and another atom gaining electrons. So remember the sodium chloride, where sodium lost one and chlorine gained one, and now they were charged? Well, those are called ions. And ionic bonding occurs between oppositely charged ions. The cations are the positively charged ions. I kept that straight for several ways. When I was growing up in cartoons, when a cat was run over by a car or something like that, when it was chasing a mouse, it would show the cat laying there with pluses in its eyes for being a dead cat. And so the cat eyes had a plus. Someone else mentioned that cation has a T, which is also a plus. So cations are positively charged ions, and ions are the other one. They're the negatively charged. So you see chlorine and hydroxyl ions here, they're negatively charged. And like it says, occurs between oppositely charged ions. So sodium is attracted to chlorine, sodium chloride. Hydrogen is attracted to hydroxyl for making water, that kind of stuff. Calcium is attracted to two chlorines because it has two pluses. It can accept two negatives. It'd be calcium chloride, CaCl2. Here's an ionic bond example. It's showing how ions were formed and then they're attracted to each other. So we saw this before. Sodium lost an electron, chlorine gained one. So look at the definition. This results from the formation of ions, ionic bonds do, from the gain or loss of electrons from atoms in order to have a complete outer energy shell. Oppositely charged ions attract each other. That's oppositely charged. This electrical attraction is called an ionic bond. So you have sodium here with a plus in there and chlorine with a minus. That's how they're attracted. It's an ionic bond. There is no gaining or sharing of electrons here. The ions have already been made and they're attracted because of their charge. Sodium is positive, that's attracting to a negative, chlorine. Just like a positive and a negative pole of a magnet, they attract each other. The same poles, positive and positive, repel. But positive and negative attract. That's an ionic bond. It's a charge attraction. Here is showing calcium chloride. Remember I told you that we would only go to the fourth shell once. And you see the calcium's element number 20, so 20 protons in the nucleus, and has 20 electrons in a neutral atom of calcium. And I've drawn the neutral atom here first, and I drew each of the chlorines with 17 electrons because they have 17 protons. But we know that calcium, having 2 out of 8 in its outer shell, is going to lose those. And so when it loses those electrons, it's going to be Ca++. It has 2 more protons than it has electrons. So you could write that like initially 20 protons and 20 electrons. Overall net charge is 0. When it loses those 2 electrons, it's going to be 20 protons, 18 electrons. So it's got 2 more positive charges. So you put calcium++. You know when chlorine was 17 protons and 17 electrons, and overall net charge is 0. Well, when it gained an extra electron, now it's 17 protons, 18 electrons, 1 more negative charge than positives, so it's Cl-1. Calcium being +2 can attract 2 negatives, so that's CaCl2, calcium chloride. When we talk about weak attractions, we're only going to talk about really the hydrogen bond. It's a weak attraction. Let's look at the next slide. Our hydrogen bond, a weak electrostatic attraction between a hydrogen of one molecule and a strongly electronegative atom, oxygen or nitrogen of another molecule. And we see right here that nitrogen's forming a hydrogen bond with the hydrogen of this water molecule here. Electronegativity, the measure of attraction of an atom for electrons. So it has a very strong pull, and so it's going to form a hydrogen bond with the hydrogen of that water molecule. Water molecules, we'll see later, form hydrogen bonds with the surrounding water molecules. So we will see that in the future, each water molecule can form or have 4 hydrogen bonds around it, each molecule of water. Okay, some terms here. Some things. Surface tension of water is due to hydrogen bonding between water molecules. Well, remember I told you each water molecule can have 4 hydrogen bonds around it. That's the surface tension. Try doing this, and because you can see this. You've seen insects walk on top of water before. You've seen debris like sitting on top of water before. And that's due to the surface tension. There's not enough pressure to break those hydrogen bonds. Try doing this. Get a glass of water and fill the glass with water, and then let it add drops one at a time. And you'll see that the water actually comes up above the top of the glass. That's because of the surface tension. The water molecules have their hydrogen bonds between themselves, and they can hold themselves together for just so long. But when that one drop goes on there and there's too much force pushing on the sides of the water trying to flow, too much pull, you'll see it dribble, and then it reforms itself again, and it still will be above the glass. Capillarity, the attraction of water molecules to a wettable surface. Well, to a wettable surface like cellulose. Well, cellulose is a polar molecule, and polars attract polars. So I have cellulose and paper towels as a polar molecule, and hydrogen bonds can form. That's why paper towels are used to pick up spills like water, because cellulose is polar and water is attracted to polar molecules. And so water is pulled up into that cellulose paper towel. It's attracted to the cellulose in that towel. Hydrophobic interactions. Hydro is water, phobics, phobia, or fears. Molecules are repelled by water, like lipids. Hydrophobic molecules are nonpolar. They are nonpolar. Polars attracted to polars because of the charge, positive and negative ends. But nonpolars are not attracted at all to polar molecules, and so they're basically repelled, and they're called hydrophobic molecules. Here are some shapes here, molecular shape and function. If you look at the bottom middle picture here, the bottom of the middle picture, it shows methane. This is a gas, carbon and 4 hydrogens, CH4. And you know that there's a single bond between each of the hydrogens and carbon, so there it is. Now that forms this picture at the very top called a tetrahedron. Okay, that's a specific shape. It's a pyramid shape, and that's the shape that it forms. Methane exists in that structured form, and that gives it its properties, its chemical and physical properties. It's a gas, right? We use it for cooking. Now you look at the middle picture here and you see water, H2O. Now the hydrogens are not exactly on opposite sides because of the polarity thing going on here, and there's a degree here, 104.5 degree angle between the hydrogens in that molecule. That gives it a specific shape in space. That also affects its chemical and physical properties. Okay, so we have a molecular shape and function. Shape is involved in the function of the molecule. They have to be specifically shaped to do what they're supposed to do, just like a lock and a key do. You can have a lot of keys, but they don't all fit the right lock. Well, they have to be the right shape to fit that lock. So these molecules, they form a shape, and they can have certain interactions with other molecules because of their shape. It's very important. Here's a molecule called a mimic. Now, endorphins are natural molecules produced by the brain. They're painkillers, and they typically make you feel relaxed, and they can block pain. When you've had a real satisfying meal, you probably notice you get kind of sleepy. That's because your body's producing endorphins to relax you. If you look at the little box there on endorphins, And you see this, the molecular shape here. It has carbons, has hydrogens, has oxygens there and there. And you look at the molecule on the right-hand side, morphine. Morphine, that part of that molecule is almost exactly identical to the structure on this endorphin. Now, endorphin blocks the transfer of pain impulses. They can't be transferred from one neuron to another neuron to be registered as pain. It blocks something called substance P from being released. Well, morphine is almost identically shaped to endorphin, and it mimics the effect of endorphins. And you know that we use morphine to block pain for surgery or for certain types of pain. They use morphine to block it. That's why it mimics the effects of endorphin, and so it can block the transfer of pain. So if you have surgery or something, they'll put you on a morphine drip to ease the pain. It blocks most of it. Here is something, this says chemical reactions. We have two hydrogen molecules here on the left, a molecule of oxygen there in the middle, the two reds. You see there's your double bonds there between them, and because they're forming little white tubes for their bonds, okay? Two hydrogens and one oxygen makes water, H2O. So you have two molecules of water that were formed because of these addition of these atoms. And there's the molecules with their 104.5 degree angle between the hydrogens there. The reactants and substrates. The reactants and substrates on here, this is not the best way that I draw it. Look at the next slide. I guess there we go. Reactants to substrates. You have reactants like sodium and chlorine make a product, sodium chloride. This is how you write the reaction down linearly like this. You could put H2 plus O, 1/2 O2 makes H2O. Okay, you can do that. You can put H plus Cl makes HCl, hydrogen chloride for hydrochloric acid. This is a reversible reaction, and it's not written correctly. This is evidently an old slide set. I need to get a newer slide set up. But this would be like if you wrote A stood for adenosine diphosphate plus B is phosphate, can be put together to make a molecule ATP, which is AB here. Well, ATP can be broken down, go to the left, to form ADP plus the phosphate, and there's another one plus energy could be released also. You'll see that on future slides though. This is a reversible reaction, and the arrows should be a half an arrow going left and a half of an arrow going right. Not the full arrowhead, but half of an arrowhead. Chemical equilibria. This is where molecule A and B on this side can be converted to C and D on the other side, and C and D can be converted to A and B. So they kind of monitor each other. They keep each other in equal levels. So these are reversible reactions also. So it'd be half arrows on both of those also. We're not going to be talking about really anything about this type of a chemical equilibrium though. Some more new terms, oxidation and reduction. Oxidation, the removal of electrons from an atom or a molecule. Remember when sodium gave up its electron? It was oxidized because it lost an electron. So the removal of electrons from an atom or a molecule, that's oxidation, loss of electrons. Reduction is the gaining of electrons, the addition of electrons to an atom or a molecule. Oh, remember chlorine accepted an electron. Chlorine got reduced. So while sodium lost an electron and got oxidized, it made a cation, Na+. Chlorine was reduced when it gained an electron, and it made a negative ion called an anion, Cl-. So oxidation is the loss of electrons, reduction is the gaining of electrons. Now here's something that's kind of important here. We'll get to this a little bit more later. In living cells, oxidation almost always involves the removal of hydrogens also, and reduction, the addition of hydrogens. That's because there is a carrier molecule that picks up the electrons. It also picks up some hydrogens and transfers them somewhere else. And we'll see that on another slide set later. This image was here just to show you, again, for oxidation and reduction, how sodium is getting oxidized, it's losing an electron, and chlorine is being reduced because it's gaining an electron, and these will form ions for an ionic bond.